Everyone. My name is Muhammad Daud, and together with my teammate, we will be presenting our project title Washington State Electric Vehicle Classification BEV versus PHEV. Introduction and motivation of our project is electric vehicles or EVs have become a key part of global effort to reduce greenhouse gas emission and transmission towards clean transportation. Governments around the world, including US, are investing heavily in this sector. Washington state is particularly is one of the leading in EV adoption. It has thousands of registered vehicles across the battery electric vehicles, which are fully electric, and plug-in hybrid electric vehicles, which is also known as PHEVs, which are both electric and also utilize the gasolines or petrols. Understanding the difference in these vehicle types is extremely important. For example, policymaker can decide whether to install fast chargers, utilities that can plan electric demand, and car manufacturers can track which model are the most popular and efficient in different regions. So the goal of our project was simple and powerful. To use machine learning automatically classifies each vehicle as BEV or PHEV based on real registration data of that is collected from Washington state. This kind of classification helps us build clearer picture of EV adoption trends, energy use, and potential future infrastructure needs. Coming next to our topic, we now will look at the data that we have used in this as a data set. So the data set comes from a Washington State Electric Vehicle Population Data 2025, a publicly available and regularly updated record of all registered EVs in that state. It contains over 3,99,000 records after we balance the data, which makes it very large and realistic data set from analysis. Each record represents one electric vehicle that and includes details like make, model, for example, Tesla, Nissan, Leaf, Toyota Prius, and others. Location information is also like city, country, latitude, and longitude, electric utility providers, which help us understand the regional electricity supply, and the CAFP eligibility. This tells us whether the car qualifies for the Clean Alternative Fuel Vehicle program, which offers government incentives. Numeric features such as model year, base, manufacturer suggested retail price, and electric range. The target column we aimed to predict was electric vehicle type, which was represented as 1 for the BEV and 0 for the PHEV. We both, so dataset analysis is coming to next slide. We're gonna explain that before training our model, we had to make sure the dataset was clean and consistent. We began by exploring all the columns to understand the infrastructure of the data. During this exploration, we noticed some missing values in the numeric and categorical columns. A few outliers in price and range, such as unusual high electric range and likely represented data entry errors. Some duplicates that we needed to be removed. To fix these, we use a systematic approach. Missing values were replaced with medians because the median is less sensitive to outliers. This way, we avoided losing important data while still keeping consistency. We also discovered that BEVs and PHEVs were not evenly distributed. BEVs were slightly more common, reflecting Washington's growing preference for fully electric vehicles. To handle this imbalance later, we used a resampling technique called SMOT, which with my partner will explain. The dataset also had a wide variety of makes and models from Tesla, Nissan, BMW, Toyota, Ford, and Chevrolet, and spread across dozens of countries. This diversity makes our model more generalizable and helps it work well for other different regions. Finally, we visualize distribution for distribution of features like model year and electric range. Most EVs were manufactured after 2018, showing how rapidly new models were being adopted. In short, this exploration confirmed that the dataset was rich, detailed, and ideal for building a classification model once properly cleaned and balanced. So far, we looked at the purpose of our study, the data source, and we cleaned and analyzed it. So for the next for my slide, I'm going to hand over to my teammate who will explain how we process the data further, train the machine learning model, and evaluate the performance. Thank you.
Thank you so much. Now I will explain further and I will explain the feature selection and engineering. After cleaning the data, our next step was feature selection and engineering, which is one of the most important parts of any machine learning projects. We started by identifying which variables were truly relevant for predicting the type of electric vehicle. Based on domain knowledge, we selected both categorical features such as make, model, country, city, electric utility, and CAFV eligibility, and numeric features like model year, base, MSPR, electric range, latitude, and longitude. The logic was straightforward. The make and model help capture design or brand preference. Base MSPR and electric range relate directly to technology and cost. Location and utility provider reflect geographic and infrastructure factors. We also perform feature engineering to improve data quality. The vehicle location column, for example, contained text strings with coordinates. We extracted latitude and longitude from those strings to use them numerically. Any missing coordinates were imputed with median values since median reduces the influence of outliers. Finally, we removed identifiers, fields such as VIN and vehicle ID. There are unique numbers that would make the model memorize rather than learn patterns, something known as data leakage. This stage gave me a focused, meaningful dataset that connect vehicle, price, range, and geography to the EV type. Now I will move next to the next slide. It's transformation and pre-processing. Once we had our selected features, we prepared them for machine learning through data transformation and pre-processing. Because our dataset had both categorical and numeric features, we used two techniques. One, hot encoding. This converts text categories like Toyota or Silter into binary numeric columns that the algorithm can understand. And we made sure to use parameters that prevent errors if unseen categories appears later. The other one is like standard scalar. These standardize the numeric variables such as base MSRP and electric range so that all features had a similar scale. This step prevents large values features from dominating the model. After encoding and scaling, we checked for any remaining non-values and replaced them with 0. We then tackled a common challenge in real datasets: class imbalance. Our dataset had more BEVs and PHEVs which could bias the model. To fix this, we applied SMOT, synthetic minority oversampling technique, which intelligently creates a new synthetic samples of minority class. As a result, the final dataset was balanced and contained more than 1300 features after encoding. This may sound large, but it typically for machine learning, and it allows our algorithms to capture relevant pattern in the data. Now I move to the next slide, which is like algorithm and model testing. We evaluated multiple algorithms to compare accuracy and interpretability. Decision tree, random forest, Bayes artificial neural network, and LSTM neural network. We applied randomized C for tuning and use an 80-20% train test split stratified by target class. The neural network models trained for 10 epochs each. This combination let us assess both traditional machine learning and deep learning approaches for EV classification. Now, my next slide is like model performance evaluation. After testing all models, achieved very high performance and ROC AUC score closest to 1.0, showing that our features and pre-processing was extremely effective. This random forest and decision tree models performed best overall. They achieved the highest F1 score and were easier to interpret compared with deep learning models. Moving on the next slide, which is like confusion matrices. Now let's interpret the confusion matrices shown here. Each matrix visually compares the model predictions with the actual vehicle type. The row represent the true values, BEVs or PHEVs. The column represent with the model predicted. The diagonal cells contains correct classification with the off diagonal cells show misclassifications. As you can see, most of our results are concentrated along the diagonal, meaning the model made very few mistakes. We achieved extremely high positive rate, correctly identified BVs and true negative rates, correctly identifying PHEVs. This confirms that the model are not just accurate overall but also balanced. They perform equally well for both classes. In practical terms, this means the system could accurately predict the type of new vehicles being registered in the state. And my last slide is the conclusion. All the five models performed exceptionally well, but random forest and decision tree clearly stood out. They offer both high performance and interpretability, which are vital for real world policy and industry applications. The main success factors behind the results were through feature engineering that captures the most relevant vehicle and geographic attributes, careful data standardization and balancing using smart, systematic model tuning, and evaluation across multiple algorithms. Overall, the classification pipeline is both robust and scalable, making it suitable for ongoing EV population studies or policy analytics. For Washington State, such predictive models can guide infrastructure planning, such as where to install public charges, economic forecasting by understanding adoption trends, and environmental decision making by linking EV data to emission reduction goals. Thank you so much.